I will attempt to summarize what you learned in probability now. Okay, first thing I want to touch on is this definition of probability. What is the definition of a probability? Now, I give you an example, maybe illustrate example. Probability of getting a head. If you toss a coin is half. Now, what is this half? This half essentially is the, if you toss enough times, you toss 100 times, toss 1,000 times, toss a coin 10,000 times. Actually, this is the limiting frequency of the event. Now, this may sound very complicated, but actually it's not. All we are saying is you toss enough, many times, ultimately, you half of the time you'll get hit. It doesn't mean that you toss 5 times or 6 times, always you get 3 times you will get hit. But not the key word here is limiting. Right? Not 3 times, not 5 times, not 10 times, but many times. Got it? So we get the idea of limiting frequency of an event. That is actually probability. Now, very often you see this. The second point I want to talk about is this. We say probability of an event A equals to NA over NS. What is NA? Maybe I can explain. NA is the number of outcomes corresponding to the event A. NS is the total number of outcomes. Now, this can only be true. Let's say, for example, I mean, if I use as an example, here, throwing a fair die. Correct? Let's say I throw a fair die, then I get probability of an even number. Got an even number. Even number, how many outcomes that correspond to this event called even number? There are 3, right? Because you have 2, 4, 6. What is the total number of outcomes? 6. I think this one is easy. Now, but there's an important condition I want to highlight. This is only, you can only use this formula. Guess what is it? Only if the sample, only if the sample space S, this is the total number of outcomes, like sample space S, consists of a finite number of equally likely outcomes. The keywords are equally likely. So which means in my example, the important word is a fair die. Now, if the die is not fair, there's no way this 3 over 6 applies. So I want to emphasize that. Got it? Yeah. Okay, good. Next, in probability, we also use the multiplication principle. Okay, remember what is multiplication principle? You will do one, you use multiplication principle if it happens one after another. Let us use an example 2, which is in your notes, but I modify it a little. Let me type it. 2 books are taken at random from a shelf containing 5 paper bags and 4 hardbacks. What is the probability that one is a paper bag, this I modify a little, and one is a hardback? That means you choose 2. Yes. What is the probability that you take 2 at random from a shelf? So the answer is this. You use multiplication. I'm going to illustrate how we use multiplication principle here. The answer is this. If you take two books, the first book you take, you will get the probability that it is a paperback is 5/9. Now, when you take two, it's inherent that they do that. Never say you take one and then put back, pick one, put back. Actually, you take two at one go. It's the same as taking one after another. So it's 5/9. This is the probability. The first one is a paperback multiplied by the second one is a hardback. Actually, it's 4/8. I'm illustrating the use of multiplication principle. Again, I say you use multiplication principle when you do one after another. There's a sequence, the first one, the second one. Now that's not all. Actually, you must consider this is the probability that the first is a paperback. This is the probability that the second is a hardback. It could be first one hardback, second one paperback. It could be, I'm again using the multiplication principle because this probability is the probability the first is a hardback. This is the probability that the second is a paperback. Now I want to emphasize again, we use multiplication principle when it's one after another. And whenever we use multiplication principle, we always have an order here on probability. Good? Of course, some of us will say this thing is actually the same as this just one term times 2. Fine. If you can see it, well and good. All good? Yes? Okay, next. Now, there is another way to solve probability problems. For selection without replacement, we can use P and C also. What do I mean by P and C? That means the NCR method. Now, let me copy and paste the same example now. Same example. Okay, which is this one. I'm going to use the same question. All right, I'm going to use P and C. What do I mean by P and C? Now, let's think about it. You have 9 books. Paperback 1, paperback 2, all the way to paperback 5. Hardback 1, hardback 2, all the way to hardback 4. Now you're going to pick 2 at random. I am going to use the idea of probability of an event equals to number of events, number of outcomes corresponding to A divided by this. Now, when I pick 2 at one go, I'm going to use NCR here. When I pick 2 at one go, out of the 9 books, what is the total number of ways I can pick 2 books out of 9? Answer is 9 choose 2. Again, I repeat, I'm using this principle. Total number of ways, total number of outcomes when I can pick 2 books here is this. So far so good. Now, if I want to pick 1 paperback and 1 hardback, 1 paper and 1 hardback, how many ways can I pick 1 and 1? And I notice when I say choose, that means the order I did not take into account the order. That means you have P1, P2 is the same as P2, P1. I didn't count them as separate. So in your numerator, you also cannot count them as separate. So what I'm interested in is how many ways can I pick 1 paperback and 1 hardback. Actually, is 5 choose 1 times 4 choose 1. I want to contrast these 2 problems. You may want to pause the video a while and think. The method here, there is no times 2. I repeat one more time. This one, I don't times 2 because in your denominator here, I already did not take into account the order. I didn't take into account the order, so your numerator cannot take into account the order. Whereas in the above example here, when I say times and times, there is an order we talk about, that's why it times 2. This is a very common confusion. Pause the video a while and think. Okay, I'm going to move on. There are some important results that I need you to know, but do you need to memorize? I give you answer first. Oh, no need to memorize. Okay? First one, probability A union B equals to probability A plus probability B minus probability A intersect B. I think the reason why I say no is because you use the Venn diagram and you can easily think that it's logical. If I take probability A and then and then plus probability B, I double count this sum once. So I must minus away the shaded part to get probability A union B. Got it? Next, B. There's some results. This one, actually, these are not called formula. What is probability A? Probability A is probability A intersect B plus probability A intersect B complement. Sometimes you will use it. Does it make sense? Let me just draw it again. What if you have A and you have B? Probability A, which everything inside here, actually is this one, probability A intersect B, plus probability A intersect B complement. The red one is A intersect B complement. Of course. Yes? Last one. Some useful results. Really just useful. C. Probability A complement intersect B complement is 1 minus probability A union B. Again, may not look obvious, but if I write it out, it makes... There are some more, but these are the common ones. You see, A and B. I want A complement to intersect B complement. It means outside A and outside B. Therefore, does it make sense that it is actually this one? This is A complement intersect B complement. So obviously it is one whole minus everything that is inside A and B. So I don't think you need to memorize, just something that for us to think about and make use of, and know that you have seen it before, then after you use, you just derive it. Next, conditional probability. This is the one that many of us are very confused about. I want to use the example because it's a very good example in the notes. 2 cards are drawn at random from a deck of cards without replacement. That means one after another. What is the probability that both are diamonds? Now, let's take a look. The first card you draw can be a diamond, can be others. And I think it's not difficult to tell me that this is 13 out of 52. This is the probability that the first card is the diamond. This is the probability that the second card is a diamond. Again, I want to say, this is the probability that the first is a diamond. Now, then you draw the second card. I want to focus on this branch here. The second card could be a diamond also. Correct? So you draw a first card diamond. And the second card could be a diamond. And I don't think it's difficult also for all of us to see that this is... After you draw one diamond, you are left with 12 diamonds. So therefore, it is 12 out of 51. This is the one we are talking about here. Now, 12 out of 51 is not difficult. So probability both are diamonds is actually first card diamonds and second diamond is just this one multiplied by this. We're not going to do that here, but I want to take a look. What is this? What is this probability? Before I answer that question, then we take a look. What if your first card is not a diamond? What is the probability that the second one is a diamond? Because you don't draw a diamond the first one, you are still left with 13 diamonds out of 51. Correct? So, what is this probability and what is this probability? Alright, I want to say that these two, here, this one, I want to type it up. Okay, note 12 over 51 and 13 over 51 are all conditional probabilities. Conditional probabilities. Why do I call them conditional probability? Because 12 over 51 is actually the probability. I write down 12 over 51 is actually the probability that a second card is, sorry, maybe I shouldn't, yeah, let it. Probability a second card is a diamond, given that your first card must be a diamond first. That's why you are left with 12 cards, 12 diamonds left. So given that the first is a diamond, this idea is super important. Had the first card not been a diamond, which is here, then the second card, the probability that the second card is a diamond is 13 over 51, is not 12 over 51. Get it? So, therefore, this, if I were to term it like that, then if A is the event that the first card is a diamond, and B is the event that the second card is a diamond, then I want to say that actually 12 over 51 is actually probability B given A. This is the probability that the B is the event, the second card is a diamond, right? Probability B given A. Make sense? Given that the first has happened, it's like that. And we can also safely write down probability A is 13 over 52. There's no question. First one diamond is definitely 13 over 52. Then what about probability A intersect B? Intersect means what? Means they happen. A, that means A first is a diamond and second is a diamond. It is actually 13 over 52 times 12 over 51. I think this one is a branch of multiplication principle. More importantly, then we can observe that this is actually probability A. This is actually probability B given A. Which actually brings us to this very important result that we always see. Look, here. That we always see. That probability, now I rewrite probability A intersect B is actually probability A times probability B given A. Which means I rearrange, I get probability A, B given A is probability A intersect B divided by probability A. This one you see all the time. Of course, the other one, the other form that you usually see is also probability A given B. Now, of course, you just swap the two letters, you get probability A, B intersect A and A intersect B are the same. So whichever form you choose, they are the same. Now I want to emphasize, whenever you see a tree diagram here, this kind of tree diagram, this branch here that you see is a conditional probability, given that the first happened. Okay, all clear? Then, when you solve problem, this formula always comes into play. Always. Got it? Now, next. Independent events. What are independent events? This idea of independence. Right? Independent events. Now, read here. Two events are independent if an event of one has no influence on the occurrence of the other. I give you an example. I always like to give this example. Example. If A is the event that I max for breakfast, and B is the event that you eat max for breakfast. Say tomorrow. We are all staying at home now. Okay? All stay home. Your home and my home obviously different. A and B are independent events. Whether I eat or don't eat doesn't matter. We won't influence each other. Quite obvious, right? Good. Now, so does it make sense that if A and B are independent events, then if A and B are independent events, then probability A given B, what do we think? It means, given that B has happened, what is the probability of A? Given that you eat McDonald's for breakfast, what is the probability that I eat McDonald's for breakfast? That condition is not important. It wouldn't affect me because it will be the same as the probability that I eat McDonald's for breakfast. Similarly, probability B given A. Now, given that I eat McDonald's for breakfast, what's the probability that you eat McDonald's for breakfast? Surely it won't affect each other. Definitely it's probability B. As a result, if A and B, this one should come here. If A and B are independent, let us plug it into what the result we have earlier. That means this one. Plug it into this one. Let's use this one. If A, this is true for all events. Now, if A and B happen to be independent, then the left-hand side is just a probability. I write down. If A and B are independent, then probability A given B is just probability A. Correct? Then, which means I make probability A intersect B the subject. Correct? I make A intersect B the subject. It's actually probability A times probability B. Now, this result is only true if A and B are independent. So, here, if A and B are independent, then I can say that probability A intersect B is probability A times. This is a very, very, very useful and important result that we need to know. It is very often the question asks, how do you know whether they're independent? Then you say, okay, if I can prove this, then they are independent. Got it? Good. Final one. Mutually exclusive. I think this one is easy. Two events are mutually exclusive. It cannot happen at the same time. Correct? For example, if A is the event that you have 3 siblings and B is the event you have 2 siblings, these 2 events are mutually exclusive. You either have 3 or don't have 3, which is you have 2 or 1, doesn't matter. They are mutually exclusive. They cannot happen at the same time. Doesn't necessarily mean complementary, but they are mutually exclusive and they cannot at the same time. And this is the most important. This one will happen because A intersect B, it will be 0. That means you have two distinct. This is your A and your B. Your Venn diagram will look like this. Let us contrast between independence and mutually exclusive. If it's independent, doesn't mean that they are mutually exclusive. Let's use the example. You eat McDonald's for breakfast, I eat McDonald's for breakfast. They are not mutually exclusive. You can eat, I can eat, doesn't really matter. Then you ask me, how does the Venn diagram look like for A and B if A and B are independent? It can be like that, of course. But if C and D are, this one A and B are independent. If I tell you another two events, C and D are not independent, that means they depend on each other. That means maybe C is the event that you eat McDonald's for breakfast, D is the event your sister eat McDonald's for breakfast. They are not independent. And their Venn diagram can still look like this. So you cannot tell from the Venn diagram whether they're independent or not. Alright? Now what is the difference then between mutually exclusive and independence? This is given in the notes as well. So I just want to very, very quickly mention. Now, intuitively, two events are independent if they don't affect each other. They don't affect each other at all. So, McDonald's, you and me. What about mutually exclusive event? It just means that they cannot happen at the same time. What about definition? This one I mentioned earlier. They are independent if A given B equals to probability A, probability B given A is B. And I would, later on there I talk about the intersection. Mutually exclusive just means a Venn diagram is like that. Probability A intersect B is actually equals to 0. Alright? Which means this one. A and B are like that. Next. Like I said just now, if A and B are independent, then this is a very super important result. If and only if. That means if this is true, then this is true. Correct? If the first line is true, then the second line is true. If the second line is true, then the first line is true. If A and B are mutually exclusive, then A intersect B is 0, which means probability A union B is this. I think you don't need to specially remember this result. You see the Venn diagram above there. See this Venn diagram and you will know. Finally, as I mentioned just now, if two events are independent, it cannot be represented on a Venn diagram. It will just be like any two events. And this one is like that. Mutually exclusive just means that it is like that. Okay, that's that. I hope gives us a quick overview and we can try the tutorial.